Last time, I had given this problem to prove that the derivative of cos x is equal to minus sin x from first principles. So let us do that now. For this, recall that cos of a plus b is equal to cos a cos b minus sin a sin b. If you recall how we obtained the derivative of sin x from first principles, you'll remember that we have used sine of a plus b over there because you have the sine of x plus h term. So similarly, we'll have to use cos of a plus b here. So writing the expression for derivative of cos x in the limit form, we have cos of x plus h minus cos of x divided by h in the limiting case where h approaches 0. So now obviously you have to use this for expanding cos of x plus h. So we have limit as h approaches 0, cos x cos h minus sin x sin h minus of cos x, that is this term, divided by h. Now, as before, we observe that cos x is common here. So in the case of sin x differentiation, sin x was common. Here you have cos x common. So these two terms, the first term and the last term, are taken common. So we have cos x times cos of h. Remember, this is not the hyperbolic cosine function. This is cos of h minus 1 because this cos x has been taken common. So that is minus 1. And I will separate the numerator into two parts and write the denominator for each. We have minus sin x times sin h divided by h. This is this term. Now we can evaluate these separately as limits. Both these, remember that h is the variable in the limit, the variable that is approaching, in this case, 0. X is constant when you're evaluating the limit. So here we have cos h minus 1 upon h, and here you have sin h upon h. Both of these limits independently exist and are finite. So by a basic property of limits, we can evaluate these separately. So we know that this as a limit approaches 0. This is something we have done before. And this is a limit approaches 1 as h approaches 0. So the first term here is cos x multiplied by 0. So that's gone. And you have minus sin x multiplied by 1. And therefore you have only minus sin x. Okay. So that's why derivative of cos x is minus sin x. From first principles, we can prove it this way. Now, let us look at some properties of differentiation. We have been finding derivatives using first principles, that is using the limit definition. And obviously that is tedious even for a simple function, especially when you have to do, for example, a series expansion or binomial expansion, as in the case of x to the power n. Series expansion in the case of e to the power x. Although we have some results from evaluating limits before, so we directly applied those. Similarly, in the case of sin x and cos x, we had already evaluated some limits of the form sin x by x or cos h minus 1 by h. So using those, we were able to reduce the work a little bit by remembering those results. But even otherwise, even with that, we still had to do some kind of expansion of that f of x plus h term. Either it was binomial expansion or it was using the properties of trigonometric functions. So clearly, if you have a more complicated function, such as e to the power of cos inverse x or tan of 1 plus sine x, something like that, you may not even be able to find the proper expansion of that and observe the patterns in that, so that you can reduce it to some known limits or to some limits that you are able to evaluate. So luckily, we have some properties of differentiation that enable us to differentiate these kinds of complicated functions, or actually composite functions and products of functions, without going back to first principles every time. So let's look at some of those. So the basic property of differentiation is linearity. In fact, this is one of the most important properties of differentiation and what makes it so widely applicable. So linearity in general means that if you have in a simple case, if you have a sum of many things and you're doing some operation on that, then it's enough to do the operation on each of those summands, that is each term in the summation, and then take the sum of all the results. Similarly, one more aspect of linearity is if you have a constant scaling of a term, so you multiply it by some 2 or 3 or some unknown constant, and you want to apply the whatever operation is there on it, it's enough to apply the operation first and then scale it. So we can write this in a combined form. In this case, differentiation is the operation that we are talking about. What it says is, if you want to differentiate a linear combination, this is called a linear combination, a linear combination of two functions, f of x and g of x. So that means you multiply a of x by some constant a, multiply f of x by some constant a and multiply g of x by some constant b, and then add these. This is called a linear combination. The linearity says that if you have such a linear combination and you want to differentiate that, then it is sufficient to differentiate each of the functions and take the linear combination of those derivatives. So a d dx of f(x) plus b d dx of g of x, or another way to write this is a f prime of x plus b g prime of x, or f dash of x and g dash of x. Just another notation for derivative. Okay, so this is very useful. For example, we know that the derivative of x to the n is n x to the n minus 1. So derivative of x cube is 3x square, derivative of x square is 2x, and derivative of x is 1. Derivative of 1 is 0, because 1 is x to the power of 0. So derivative of x to the power 0 is 0 x to the power 0 minus 1. So that 0 times whatever it is 0. Another way to see that the derivative of a constant is 0 is, what is the meaning of derivative? Rate of change. But a constant is exactly something that does not change. It is invariant or constant. So the derivative of a constant must be 0. If the change itself is 0, the rate of change is also 0. Okay, so keeping that in mind, how do you differentiate a polynomial? Let's say I'll take a concrete polynomial now. So let's say 4x cube minus x square by 2 plus 3x minus 1. do we do this using first principles? That will involve 4 different terms to which you have to apply x plus h, replace x by x plus h, and here you will have x plus h whole cube, x plus h whole square, x plus h, expanding all these, combining the like terms and cancelling out, and then finding the limit. That's a very laborious process. Luckily, we have this linearity property, which says that it is enough to differentiate each term separately and add the results, or not add exactly, take the same linear combination. So 4 times of the derivative of x cubed and so on. So if I write it stepwise, it is actually 4 times d dx of x cubed minus, so what is a constant here? Minus 1 by 2. So minus 1 by 2 times d dx of x square plus 3 times d dx of x, that is dx by dx, well, minus d dx of 1. Here the constant is minus 1. We have a minus, right? So that way. Now d dx of x cube is 3x square. So that 3x square multiplied by 4 is 12x square. Here x square derivative is 2x. There's a minus half here, so minus half times 2x, that's just minus x. Here you have dx by dx is of course 1, and this is 0 because it's derivative of 1, or derivative of any constant is 0. So ideally you should be able to go from here to here directly without this step. Like this is an example, but once you understand this rule properly or get used to differentiating, you should be able to see this and write this down right away. Let's see one more example where there are other functions. We want differentiation of e to the power x by 2 minus 2 sin x plus x to the power of 9. So now let me write it without this intermediate step by looking at the terms. What is the derivative of e power x? E power x itself. E power x is a function that is invariant under differentiation. So you get e power x itself. What is derivative of sin x? So I write this minus 2 immediately because I know that's going to be there, and then just differentiate sin x to get cos x. Then here you have just plus x to the 9, so that becomes plus 9x to the 8. That 9 coming from the differentiation of x to the 9. So n x to the n minus 1 when you differentiate x power n. So this is how you should write the answer, and you have something like this. Okay, so that's linearity. This is obviously a very useful property because we already reduced something complicated like this into term-wise differentiation, and if we know how to differentiate each term, we can differentiate this linear combination as well. But notice, if it had been e power 2x here, or e power x by 2, or sine 2x, then what could we have done? We cannot use linearity there because it is not f of ax, it is a f of x. So if a is multiplied to a function, and if we know the derivative of the function, so here we are assuming we know how to differentiate f of x, otherwise this will not help you. You can write this, but you cannot compute it. Here we know, assume that we know the derivative of f of x. But if you have sine 2x instead of 2 sin x, suppose it was sine 2x. We know the derivative of sine x, but that does not help us get the derivative of sine 2x unless we have some other property. Linearity does not help us in that. The next property is exactly that. It says the derivative of f of ax is a f prime ax. So this means where f prime of x is derivative of f of x. Here you need to know or understand something about the notation and about differentiation in general. When we write d by dx, this is an operator. So I mentioned in operators when I discussed linearity. Okay, so I said that this is our operator. So this is an operator, which means it takes a function as input and gives another function as output. So a function itself is what? A rule that maps values to values, a rule that takes a value and gives you a value, right? Or a function is something that takes an input value and gives an output value. Similarly, an operator, you can think of it as a function of function. So it takes a function as input and gives a function as output. Okay. So what is this differentiation operator? The one that we have been using. It takes a function as input and gives its derivative as output. So for example, if you give the function x cube as input to dx, you get the output x square. If you give 4x cube as input, you get 12x square. If you give 4x cube minus x square by 2 plus 3x minus 1 as input, clearly you get the output 12x square minus x plus 3. So this maps functions to their derivatives. Takes a function, gives its derivative. So this is the notation for that, but as part of the notation we are writing this x, right? That is very important. So this x is the variable with respect to which we are differentiating. So if you write dy dx of f of x, this has a very clear meaning, which we have not looked at very carefully before, but the definition was given clearly, so and there was no need to analyze it further. So this is clear. What we need to do given this is clear. But if you analyze this notation further, what would it mean to do differentiation of f of ax? Ax is not the variable here. You're differentiating f of ax with respect to x. So that's something different, right? But you can always think of f of ax as a new function. So let's say the g of x is f of ax. So there's nothing strange about that. For example, if you have sine 2x as your function, what we think of is sine is one function because that's a well-known function. Although it's as good as sine 2x, sine is a more well-known function. It's a standard function. So we tend to think of sine as the basic function f and sine 2x as something modified in the basic function, that is sine x. That is true. You take sine x and then multiply its argument by x, not multiply the result by 2, multiply the argument by 2. That is what gives you this new function. But this is also a function on its own, although it may not have a special name. So we can say g of x is equal to sine 2x, and this defines a new function. All right. Then that obviously works in general as well. So here what you're actually doing is differentiating this new function g of x, and then again, if you use this definition, how to compute it is very clear. You take limit h approaching 0, g of x plus h minus g of x upon h. Now this in terms of f of x can be written as limit h approaches 0. Now what is g of x? It is f of ax. So what is g of x plus h? It is f of ax, rather f of a times x plus h. That's important. A times x plus h, not simply ax plus h, a times x plus h. Whatever is here, that needs to be multiplied by a. And of course, this is f of ax. You have this divided by h. So we get limit h approaches 0 of ax plus ah minus f of ax by h. Now, if you compare these two, they look very similar, but there is a crucial difference. That is, here it is ax and here it is ah. So if you want to say that this is also some derivative, some function's derivative, you need to match this exactly. If it is x here, it needs to be x here. If it is h here, it needs to be h here. Whereas that is not true, because here we have it's partially true. We have ax here, we started with ax, and we have ax here. So that part is fine. So I can write this as, I will just denote this ax in this way to emphasize that we are considering it as one variable. Okay, so we are not thinking of it as a multiplied by x, but rather as one thing, that is ax. And that does match what we have on the LHS, which is also f of ax, where ax is in this, right? So there's no place where you have only x without a, so that's not a problem. But that still leaves the problem of h. Here it is h approaching 0, not ah approaching 0, and in the denominator it is h, but in the numerator it is ah. So what we do is multiply and divide this by a. So now in the denominator, that does not change any value because you're multiplying and dividing by a. And now in the denominator you have ah, and in the numerator there is a. That constant I will write outside. Okay, so let me put this in a bracket and write this is a, because you're multiplying a limit by a constant, you can multiply inside or outside. However, we still have h approaching 0 here, so that also I'll change and write that as ah approaching 0. Now, is this valid? Normally I cannot just multiply by a, right? That changes values, but here h is approaching 0. So as h approaches 0, clearly ah approaches 0 as well. So h approaches 0 implies that ah approaches 0 as well, and of course this in turn implies this. If this is true, this is also true, right? If ah is approaching 0, h also approaches 0. So these two are equivalent statements or equivalent conditions. So I can do this, and now this is in the standard form of derivative definition in terms of limit. Only that I have ax here instead of x. Ah can be thought of as a new variable k if you prefer. So you can say limit k tends to 0, f of ax plus k minus f of ax by k. That is of course the derivative of f of ax with respect to ax. So that is the difference. So if you think of ax as a new variable y, then this is f of y and this is f dash of y, derivative of f of y with respect to y. But there is an a outside, that still remains. So here what we get is a times f dash of ax, where f dash of x is the derivative of f of x. Okay, now let's look at an example of this. So as I said before, suppose you have sine 2x. Suppose you want to differentiate sine 2x. Now, again, these steps are not really necessary to be written separately. For the first example, I'll just write them explicitly. Okay. So you have d dx of sine x is cos x. So that's like this. F dash of x. What is the basic function that we identify here? How do you know what is a basic function? The one for which you already know the derivative. That is a basic function. So here the basic function is sine. So sine x derivative is cos x, but here we have sine 2x. So you identify this is purely matching a pattern. So it is up to you to match the pattern in a way that enables you to use this property. So you have sine of 2x, and you match that with this pattern f of ax in this way. You say that sine is the basic function f, and 2 is the constant a. So if you differentiate this, clearly this a must appear on the LHS as a factor of the final answer. So that is 2. This a is here 2. And then you have f dash of ax. So f dash is nothing but the derivative. So what is f dash? Cos. So think of it like that. F dash is cos if f is sine. But notice you don't have f dash of x. So it is not cos x here. It is cos ax. So that is 2x. Okay. It sounds elaborate when I'm explaining it, but you can see that it's very simple. And finally, when you are practically doing this, you can even think of it this way. When you are differentiating, the constant inside this function pops out. It just comes out as 2. So here 2 comes out, but it does not go away. So it comes out as an extra thing. So this 2 inside remains. So sine 2x becomes cos 2x, but the 2 comes out each time you differentiate. Take another example without that much explanation. If you have e to the 3x, this is going to be pop out the constant, so that gives you 3. And then differentiation of e power x is e power x itself. So differentiation of e power 3x will have e power 3x with a 3 in it. See another. Cos of x by 2. So this will be half times minus sine. So minus half times sine of whatever is there. X by 2 is there. Here also you have x by 2. So that 1 by 2 is a constant that has come out, and this minus is from differentiating cos. It's not from anywhere else. You can combine linearity with this property. So if you have say sine of x divided by, so let's say sine of 3x divided by 3. Okay, just to make it interesting. Now when you differentiate this, the 1 by 3 which is outside remains there because of linearity. It becomes 1 by 3 times derivative of sine 3x. Derivative of sine 3x is itself 3 cos 3x. So there is a 1 by 3 outside already. Those cancel out and you just get cos 3x. Okay. Now this property, which is also very useful like linearity, is a special case of the more general property called chain rule. So chain rule requires an even better understanding of the notation. So chain rule says that if you have y as a function of x and z is again a function of y, then firstly, what does this imply? Z is g of y, but what is y? F of x. So z is a function of x ultimately, right? It's a function of x, which means it's a function of x, some other function of x, correct? So to take an example, so that I can show you the application in parallel. Suppose you have y is equal to x square and z is equal to sine of y. What do I mean by this? Z is a function of x. How is that so? Well, then z is sine of y, which is x square. So z is sine of x square. Now, if I gave you this directly, obviously z is a function of x. Here it is just slightly obscured because y is x square and then z is sine of y. But clearly that makes z a function of x. So it's very valid to ask, what is dz by dx? If you forget this part and just think of z as a function of x, what is dz by dx? Now, how can we compute this? Does linearity help us? No, because it's not something multiplied by sine x. Does this help us? It looks similar, right? You have sine of 2x there and here you have sine of x square. But this is not sine of some constant multiplied with x. So maybe you can think of writing this as sine of x multiplied with x. But x is not a constant. That is a crucial difference. Here, a is a constant. So even if you manage to, I'm sorry, even if you manage to write it as sine of something times x, that something is not a constant. So the second property also cannot be used. So we need a different property, that is chain rule. So the question is, what is derivative of sine of x square? Now, why do we think that it may be possible to find it without using first principles? Because you can apply first principle here, but imagine how difficult that would be, or how complicated the computation would be. You would have sine of x plus h the whole square minus sine of x square. X plus h the whole square itself has an expansion, which is x square plus 2xh plus h square. Then you have sine of that. So you need sine of a plus b plus c expansion, right? Or maybe sine of a plus b expansion where a is taken as sum of two terms and then again expand. So that's going to be complicated. But it seems that we should have some other way of doing it, because we know how to differentiate sine function. We know how to differentiate x square function. So is there a way of combining these two derivatives to get this derivative without going back to first principles? So chain rule tells you that yes, there is. So it says, now given that z is a composite function of these two, g and f, and that makes it a function of x, d dx of z, that is dz upon dx, is actually dz upon dy multiplied by dy upon dx. This is called chain rule. Well, here itself it's somewhat evident why it's a chain, because you have this as a link, this dy as a link, but you can see that if you have more functions here and a larger composite function, you can extend this like a chain. So we'll see examples of that. Yes, that's just repeated application of the same rule. Now let's see what this says in this example. You have y equal to x square and z equal to sine y. So z equal to sine of x square. Now, according to this, you should first differentiate z with respect to y. So that gives you dz upon dy is cos y. And you should differentiate y with respect to x. So that is 2x. And then multiply them together. So dz upon dy, that is cos y, multiplied by dy upon dx, which is 2x. Okay, so this is the answer. So it doesn't look very nice because it looks like a function of two different variables, but the fact is that y is actually x square. So you can write this as cos of x square multiplied by 2x, or in a better form, 2x cos of x square. So why do I say this is a better form? Because it avoids the confusion of thinking of 2x being multiplied with x square. This x square is the argument of cos, so it is inside the function in some sense. do not multiply x square with this 2x outside, right? This is outside really. So when you write it this way, it's clear. You're not likely to multiply this 2x with the x square inside. So write it this way, that is better. But yes, we see that we can get the derivative of, so this is the answer here. You can get the derivative of this composite function, that is sine of square of x. So you can see the two functions there. Sine is the outer function, square is the inner function of x. Sine of square of x is differentiated to give 2x cos of x square. So ideally, even if the function is not explicitly split up in this way, and you're directly given sine x square, you can always recognize that it is actually sine of square of x. That means sine y is one function where y is x square, and then apply the chain rule. That is what we normally do. We are not given this separately in most cases. We are given z equal to some composite function of x, and we have to recognize it as a composite of functions of which we know the derivatives. We'll see examples of how to do these. Now, why is this a general case of the previous one? Clearly, this f of ax can be thought of as a composite function, where you have we wrote it before, right? We have g of x is equal to f of ax. So f of x is your basic function, and yeah, in fact, you can write it as f of y, where y is ax. So you have z equal to f of y, that is this g of x is f of y, and y is ax. So according to chain rule, what should dz by dx be? Dz upon dy times dy upon dx. Now dz upon dy is f dash of y. Okay. We can't say anything further about that because f is an unknown function. So we can say it's f dash of y. Dy upon dx, y is ax. So dy upon dx is a times dx by dx, which is a. So this is f dash of y, but that's again f a times f dash of ax because y is ax. So when you get a problem like this, as I said, you will get this directly. You won't get this split up as such. But even if you think of it in terms of split ups, the final answer should be only in terms of x. There should not be any y in it. So that's the same thing we're doing here. We have actually the function we are differentiating is f of ax. We have rewritten it as f of y, where y is ax. But in the final answer, that y should not be there. It's something intermediate that we introduced to simplify the problem or simplify the approach to the problem. So in the final answer, it should be only x. We have a f dash of ax. So this is clearly a special case of the chain rule. I'll show you one or two more examples where we don't have the splitting done explicitly. So the second example, let's have e to the power of sine x. So what is the derivative of e to the power of sine x? So now what you do here is, okay, for this problem also, let me write it as z is equal to e power sine x, where y is sine x. And so dz upon I'm sorry, that makes no sense. Let me write this function as z is equal to e to the y, where y is equal to sine x. So now we can find out dz upon dy, which is e power y, and dy upon dx, which is cos of x. Now remember, we want to write everything finally in terms of x. So this e power y is again remembering that y is sin x. This is just e to the power of sin x. And so now chain rule tells us that dz upon dx is equal to, that is this thing, is equal to dz upon dy times dy upon dx. So that is e to the sin x times cos x, or cos x times e to the sin x. Same thing, I'm just writing it in a more traditional form. Now, how can we do this without splitting it? So I'll take the same problem again, only the answer should be written differently without so much elaboration. So now this is to be only done in your mind. What you do is you put this sin x in a box and think of that box as a new variable. So e to the y, where y is sin x, is what we wrote here. This y is the box. So remember, in multiplication the order does not matter. So I can write this as dy by dx times dz by dy also. That doesn't matter. So I'll do that. I'll start by differentiating y with respect to x. So y is sin x here. So this box. So differentiation of this box with respect to x is just cos x. And then you have e to the power of sin x. But don't think of it as e power sin x. Think of it as e power y, or e power some box. And you're differentiating with respect to y, which means you're differentiating with respect to this box. Right? So in your mind, what you should be doing is derivative of e power is e power. E power what? The same thing. So that is differentiation of e power y is e power y. We directly get the answer this way. Take one more example of that with a different function. Let's have sine of x cubed plus x. So now what do you do? See, you have to recognize the pattern there. So the innermost function is this. You know how to differentiate polynomials by linearity. So you can think of this as one function. So what you have is sine of this box. So first you differentiate what is inside the box. So that gives you 3x square plus 1, simple linearity. So differentiate term wise and add 3x square plus 1 multiplied by derivative of sine of the box with respect to the box, or sine of y with respect to y, that is cos y, right? So cos of whatever is inside the box, you have to faithfully copy it. That is how chain rule works. So cos of x cubed plus x. What if you had more functions? Suppose instead of this you had sine of e to the power of let's say e to the power of cos x. So now there are more boxes. You should always start with the innermost one. The innermost one is, how do you identify the innermost one? You look at where x is there, and then whatever is applied to it immediately, that is the innermost function. So if you have two different ones, like here x cube is there and x is there, but they are summed up, right? So that is one box, because that is only an application of linearity. How to differentiate this is using linearity. So think of this as one function. You have e to the power of cos x, and then what is the next layer? The next box is, if you think of this as one thing, as x or actually y, then you have e to the power of that. So that is the next layer there. And then to that box, sine is being applied. So again, if you start with the innermost box, the differentiation is cos x differentiated gives minus sin x. Then you have e to the power of something differentiated gives e to the power of that very same thing. Finally, you have sine of something differentiated gives cos of that thing. So cos of, now Here, remember to faithfully copy whatever is there. And be careful, although cos x on differentiation becomes minus sin x, the cos x in this argument will never become minus sin x. That is here, right? That will never become minus sin x. When you differentiate it, you have to multiply the derivative outside, because you have dy by dx multiplied to it. It is not differentiated while inside the function as an argument. Okay. The final example. Okay. So maybe take a moment to try to write the answer by yourself, and then look at what I'll do. So here you have x square as the innermost function, that is square of x. Squaring is the first function that is applied to x. And then on top of that, you have sine. And then to that, cos is applied actually, but you can think of it as 1 minus of cos by linearity, because this 1 minus is not a separate thing. It's 1 minus of cos of this. And then e is applied to that. E as in e to the power, exponentiation, right? And so starting with the innermost, you have sine of x square. So x square differentiated gives 2x. Then sine of x square. So that gives cos of x square. Actually, what we're doing is sine of x square derivative is 2x cos x square. So that's an application of chain rule right there. Okay, that's why the chain rule works like that. And then you have differentiation of 1 minus cos of something. So remember, when differentiating this, again, don't think of the components of this. You've already done that. You've already finished off the components. So it is 1 minus cos of a box. Differentiated gives 1 differentiation is 0 minus cos of a box. So cos differentiation is minus sine. So minus is already there. It becomes plus sine of that box. So don't forget to copy that. Whatever is here inside the cos, that gets copied here. Okay, so that gets copied here. Cos has become sine on differentiation. Cos has become this sine on differentiation. Nothing happens to this inside argument. Okay, then finally, e to the power of another box differentiated gives e to the power of that same box. So chain rule, because you keep extending this chain. If I write it in that way, you have z is a function of y, and y is a function of x, and suppose x is a, or here I'll write w is a function of z. So x is the basic variable, then y is a function of that, z is a function of that, w is a function of that. Then your question would be, what is dw upon dx? So that's what we did here. You have three functions composed together: cos x composed with e to the power composed with sine. So this would be dw upon dz, so because z here, multiplied with dz upon dy, because z is a function of y, and then finally dy upon dx, because y is a function of x. So you can see the chain getting extended. Here it was just two functions, so we just have this. Here there are three functions, so we have three terms, and you can see that that's what we've done here. First term is this. I've written it in the opposite order here, dy by dx, that is here. Then second one is here. The last one is here. The outermost layer is here. So that is how you get chain rule. You chain them together.